Hello, Ahmed. This video is principally for you, though if I put it on YouTube, others may be able to look at it and get something from it themselves. Now, the ordinary differential equation that I want to solve for you today, I'm doing partly because it will hopefully add to your increasing knowledge of ordinary differential equations. But it may also be of interest to you because it derives it derives directly from an actual physical situation, so a physics-based situation. Excuse me, and that is one of a surge tank, basically. So just to explain, I'm I'm referring to a book called Ordinary Nonlinear Differential Equations in Engineering and Physical Sciences by N.W. McLachlan. Now um, I'll write that name down just in case you want to get it. When I can find, oh, there we are. When I can find the nib. So what you want to get is oh dear, that's a very thin nib, isn't it? I wanted a thicker line than that, and it doesn't seem to be coming up there. Right, okay. So what you want is ordinary non-linear differential equations in engineering. I'll just abbreviate this language because I don't want to spend a lot of time writing it out. So you want to get the book Ordinary Nonlinear Differential Equations in Engineering and Physical Sciences. All right. And that is by the author N.W. McLachlan. I think it's a Scottish name. And the as I said, basically, he starts off in section, I think it's section 5.171, if I'm right, if I can find where I am here. Yeah, so in section 5.171, he derives a differential equation. And I'll just very quickly quote what he says. We assume that the cross section of the reservoir is much greater than that of the surge chamber, and also that the pipe and tunnel both have uniform cross sections. And then he derives a force relationship from that, and in turn arrives at two differential equations, both related. The first one it comes to is U double dot plus 2KU dot plus AU equals D. And what he then does is he uses, let me just, I've got my glasses on so I can't see the screen very well. So he uses the substitution x equals u minus d over a, from which you can establish that du by dt is equal to dx by dt, and d squared u by dt squared is equal to d squared x by dt squared. You substitute all of that into this equation, which what I'll do is I'll call that equation 1. If I can make it look reasonably neat. So we'll call that equation 1. And so by substituting in all of this here into that equation 1, it eventually arrives at x double dot plus 2 kappa. I say kappa, it looks more like a K, but it doesn't matter whether it's a K or a kappa. But anyway, we'll keep referring to it as a kappa. So we've got x double dot plus 2 kappa x plus, well, in the book he says C, but I think it's actually a D over A, but we'll just keep it as a C for now because that's what he has, and that's times x dot plus omega squared x equal to 0. So let's just yeah, there we are. Let's right, there we are. So we call that equation 2. Right, so he gets from equation 1 to equation 2, and I'll just really quickly explain about 1 and 2 here. That when you get to equation 2, you'll note that as kappa approaches 0, then what you are left with is x double dot plus omega squared x equals 0, which produces the solution x equals a cos omega t plus b sine omega t, right? So that would be the sinusoidal motion. So when k or kappa is small, equation 2 reduces to the simple harmonic motion equation. It does actually say somewhere, and I'm just looking to see what he says, but I can't remember, but he actually does say that for small values of k, the water level, I think it is, oscillates. And that would coincide with what we see happening in this equation 2, when kappa is close to 0 or equals 0. If it's close to 0, it'll be kind of periodic, but the motion will be damped. It's only when kappa is exactly equal to 0 that you get this perpetual sinusoidal motion. Now, you can simplify equation. I think he simplifies equation 2. I haven't gone through the whole derivation. It's between pages 97 and 100, 101. So I'm now on page 99, and I haven't gone through that derivation, but he eventually arrives at a periodic case, and this is where kappa is significantly greater than 0. So here we have kappa approaching 0. Now we're going to consider, when I can find my pen, so consider, I'm just going to try and write a little bit more neatly. So consider when kappa is significantly greater than 0. Okay, so we arrive at the ODE, so non-linear ODE. It's the whole point of this video. It's a non-linear ordinary differential equation, and I shall explain why in a minute. So, and by the way, the previous case of equation 1 and equation 2 were both non-linear, and the reason is that you've got this u term coefficient in front of the u dot term, and you've got this x plus c term in front of the x dot term. So that's what makes these equations, equation 1 and 2, non-linear. And I can't remember if I said when I opened the video session. I don't think I did. I don't think I explicitly said that these were non-linear ordinary differential equations. I might have said something off the cuff to the extent that that's what they are, but I can't remember. I tend to forget things. So anyway, we go on to the next page. So we when kappa is very much greater than 0, we arrive at the ODE, and it reverts back to u, but I don't know if it's the same u as before. So it's u double dash plus 2 kappa u dot plus a u equals 0. So we'll call that equation 3. Right, okay, so, well, again, we established that this is a non-linear ordinary differential equation because of the coefficient of u in front of the u dot. If that u had been a t, excuse me, if that u had been a t, that whole equation would have been linear. So if it had been a t, because this is d squared u by dt squared plus 2ku du by dt plus au equals 0. So if that had been a t, or if there had been a t, if there'd been a coefficient of t here where the a is, or a t there, it would still be a linear ordinary differential equation. But because the variable is the same as the variable that's being differentiated, if you see what I mean, it's non-linear. That might not make complete sense, but I hope you get the gist of what I'm saying. So basically, we have to solve this equation, and he actually, I think he says a little bit about it. He says, from physical considerations, it is evident that if friction in the tunnel were large enough compared with the gravitational restoring force, for example, if kappa is large enough in comparison with A, there would be no oscillation. The method of solution, therefore, used in the previous section is inapplicable here, since it is based upon oscillatory motion with slowly varying amplitude. So therefore, the differential equation for t greater than 0 is what we have here in equation 1. And what we're considering when kappa is very much greater than 0, because this will determine the nature of the solution that we get. So let's make a start. Okay. So let's get, so what I'm going to do is solve this equation, put u dash equal to p. Now u dash is just du by dt, right? Make that a bit clearer. P is equal to du by dt. So, or therefore, d squared u by dt squared is equal to dp by dt. Right, but there's something wrong with that, because if we substitute dp by dt back into this equation, we'll have a dp. Where's my pointer gone? Right, we'll have a dp by dt here, in place of the u, but we'll also have a u over here as well as and that will be a p. So we'll have a u, a p, and a t. Now you can't have three variables in an ordinary differential equation. You can only have two. One of them has to be an independent variable, and one has to be the dependent variable. You cannot have another variable, because that is not an ordinary differential equation. And it would probably, I mean, I can't say that it would necessarily be a PDE, a partial differential equation, but you might be better forming a partial differential equation if you wanted three or more variables in. But this, for an ordinary differential equation, we can only have two variables, a dependent variable and an independent variable. So this dp by dt is no use to us here. So what we do is, we use the chain rule, and I thought I was changing to a black colour, so we put the dt there. So the dt is still there, but it just ends up being hidden. So we've got dp by dt, but we shift the dt over here, onto the in the denominator of this fraction here. And so what we write here is du and du there. So by the chain rule, d squared u by dt squared becomes dp by du dot du by dt. We know what du by dt is. Du by dt is just p, right? So I'll just get rid of that, and we'll rewrite that as d squared u by dt squared equals p. Just let me, I'm getting used to this writing pad. I'll do it all again there. So we've got d squared u by dt squared. That needs to look more like a t as well, doesn't it? So that's equal to p dp by du. So we substitute this in for the second derivative of u, and we substitute p in for the u dot, right? And what we get if we do that is, I'll write it in blue ink. So we get p dp by du plus 2kup plus au equal to 0. And I'm going to let you look at that equation for a few seconds, whilst I call it equation 4, because we've seen equations like this before, but you might not quite recognize this form. Basically, what I'm going to do is put it in this form. Right? Right. Oh dear, that's let me just write that. I'm trying to find. There we are. So minus 2k u p. Right. Okay. Still haven't got a very good kappa there, have I? Right, okay. So I put equation 4 into the form of equation 5. Now we've seen equations like this before because we solved this equation in green, equation 5, when we solved the van der Pol equation. So let me see. Can I? I'm wondering. I don't think I can cut and paste anything there. Oh, I haven't. I think it might be possible, but anyway, I don't want to. Oh, wait a minute. Yeah, cut and paste. Let's try and cut and paste that. Right. Okay. So, right there we are. Add to new page. Right. Okay. Can we move this? Yes, we can. So we've got this equation. Now, when we studied and solved the van der Pol equation, we had an equation of the form y dy by dx plus f of x equal to g of x times y. And George Moseley Murphy in his book of 1960, which is currently in print, it's currently being reprinted. He says that if, I think it's if and only if, I think dy by dx has to be equal to 0 such that a viable solution to this equation is, I'll keep it in red, is y equals f of x over g of x, right? So that is a viable solution of, let me just see, previous, so we want equation, we call this equation 6, I'll keep it in red ink, and this is equation 7. I should be consistent and just use black ink for that, but anyway. So George Moseley Murphy is saying if dy by dx here is 0, then a viable solution is this function divided by this function, right? So we can therefore extend that to this solution, and we call that equation 5, didn't we? So I'll put a 5 there. I know we've already labelled it as 5. And what I'm going to do is I'm going to cut that and add to new page. There we are. Try and line it up. Right. So I'm now saying that let's assume that a viable solution, well, we want to work out if it's a viable solution. So we make the claim that P equals AU over, and it's minus AU because this is minus. It's AU divided by minus 2KU, which obviously makes the whole thing minus. And can I go back to black? So there you can see that the U's cancel. So I'm making a claim that the solution to equation 5 is P equals minus A over 2K, right? Now you can see from that that dP by du is 0. If you differentiate both sides of this solution, you get dP by du is equal to 0. So therefore, if you substitute this and this derivative back into equation 5, you'll find that you have the following. So we'll go back to green. So we've got P, which is minus A over 2K, times dP by du, which is 0, plus AU. Well, that's the left-hand side, isn't it? So the left-hand side is equal to, this is the P term, and this is dP by du. So I'll just use my mouse because it might not light up when I use my pen. So the left-hand side of this equation is equal to P here is minus A over 2K, and dP by du is 0, and we've got this additional term plus AU, which we leave alone, and that is equal to AU. Now the right hand side doesn't need anything doing to it very much, except that you've got minus 2KU times P. Well, we know what P is. P is this. So we've got minus 2KU times minus A over 2K. Let's change colour. It's disappeared. If I move too quickly, it'll just disappear. So the minus 2K cancels with the minus 2K on the bottom and or in the denominator, and therefore we're left with AU. Therefore, left-hand side equals the right-hand side. So P equals minus A over 2K is a viable and legitimate solution. We'll write that there. Solution. Right? So, because the left-hand side equals the right-hand side when you substitute all of this in, you find that the left-hand side is equal to the right-hand side, so therefore P equals minus A over 2K is a viable and legitimate solution. Now, we've got to work back to the original equation, which is equation 3. And I'm going to cut and paste that again. So this is equation 3, and we want to cut and paste, and oh wait a minute, okay, so here in equation 3 we know u dot, I can't write to save my life, can I? So u dot has been set equal to P, but we know, let me just see if I can, here we are. So it's added the page in at an odd position in the series of pages. So we're going to substitute u dot equal to p. So what we'll have now is, let's just go back to black. So since u dot equals p and p equals, and I have to look at it, equals minus a over 2k minus a over 2k, then we've got u dot equal to minus a over 2k, or if you like, du by dt equals minus a over 2k. So we can solve that quite easily to get u equals minus a over 2k times t. Now, this is where we go back to the very first equation. U double dot plus 2ku u dot plus au. Let me just see, not that one. Next. Yeah, to equation 3. So we have to go right back to equation 3 and see if that solution that we just got, which was minus a over 2k all times t and its derivatives, solves that equation 3. So let's go back to this. So I think we have to go right up here. So u dot is equal to a, so it's actually equal to minus a over 2k, and u dot, shall I do that, write that underneath, and then I can use that space. U double dot is equal to 0. If you differentiate a constant, you get 0. So that's what u double dot is. And I'm going to rewrite the equation out, because I can't really cut and paste it because I put it on a different page. So we substitute well, let me just change colour. So we substitute all of these into equation 3, which is u double dot plus 2 kappa u dot plus a u, and see if that left hand side equals 0. So the left hand side is equal to u double dot plus 2k u dot plus a u, and if we substitute in 0 for u double dot, so here substituting u double dot equals 0, we have 0 plus 2 kappa times this u here, which is minus a over 2k, and we've got a t there, times u dot, well, u dot is this, which is minus a over 2k, plus a times u. Well, we know what a times u, we know what u is, because it's that, minus a over 2k and times t. Right, so you got 0. Well, straight away you can see that a 2k cancels with 2k there. The two minus signs cancel to give a plus. And so what we have is, and I'll write this in green, is, well, we've got a times a, or it's minus a times minus a, which is gives you the plus. So that's the plus. So it's plus a squared over 2k, and obviously we've got a t there. So, and then we add that on to this term here, which is negative, and that's minus a squared over 2k times t, and you can see that that is equal to 0. So, yeah, let's just cut that, add to new page. Right, so is a or 1 is 1 linearly independent. Actually, I'm not sure if this solution and the second solution for this equation will be linearly independent. I presume they are. They certainly say that's true of linear ordinary differential equations, but I don't know if you consider them to be linearly independent for this type of non-linear ordinary differential equation. So, but I do know there is another solution. So if you call that U1, that is our first, we'll call it a linearly independent solution. So that is our first linearly independent solution. Now, we also need to find U2. This is equal to the second linearly independent question mark solution. Well, how do we find U2? I mean, all I've said is that U2 is equal to this in words. I mean, we want to know what U2 is in mathematical symbols and in terms of an equation. Well, it's quite simple because U2 is equal to U1 times the integral of e to the minus the integral of p dt over U1 all squared and then dt. So if we plug everything we've got into this equation, we can find the second linearly independent solution. Right, but what we know what U1 is. So we know what U1 is because we've got it here. We just substitute that minus AT over 2k in for U1 here and U1 squared there. I'll just clear all those red lines off though. It makes it a bit confusing. So, but the problem is we've got this integral here. And what is P? What is P? Well, if we go back to the previous equation, but we'll just use. Let me just ring what P is. So this is. Ooh, we want red, don't we? So P is equal to the 2ku. The 2ku. So this part here. Right, so P is equal to 2ku. I'll write that down in black. P equals 2 kappa u, or 2ku. And I'm going to, oh no, I can't cut and paste it, can I? No, let's just minimize. Let me try. Might work. So Control C and right. Okay. So right. Let's Let's try and do Control V. No, it doesn't. Oh, it doesn't work, does it? I think it's right. Okay, so I'll just write it down here. Where P is equal to 2KU. But we've got a problem. We've still got a U. But no, that's no trouble, because that's just U1. So P is equal to 2K times U1. Well, we're going to have a minus sign in there. A over 2K T, right? So P is equal to, where's that gone? So that's 2K, cancels with that, and we're left with P equals minus AT. So U2 is equal to U1 minus A over 2K times T times the integral of, oh dear, I've not left enough space there, have I? Let's just go back. U2 equals U1, which is minus A over 2KT. Well, let's make that look more convincingly like an A. There we are. Times the integral of e to the minus the integral of p dt. Well, p is minus at dt, and then all of that exponential is divided by u1 squared, which is minus a over 2k t. There we are. And I'm going to have to try and cut that. Yeah, I think that should be all right. So add to new page. Okay. So we've got this. I'll just fill in where. Oops. Right. There we are. Right. Okay. So let's just fill that bit in. Right. So this can be simplified to give U2 equals minus A over 2K. We'll take the 2t outside, and that's going to be divided by a squared over 4k squared. But we'll leave, yeah, we'll leave it as, well, we'll leave it as a over 2k all squared. The minus gets multiplied by a minus, so it becomes plus. But we usually don't write that there. And that's multiplied by the integral of e to the a to dt divided by t squared, and then there's a dt. So that simplifies out to give t over a divided by 2k times the integral of e to the a t squared, because we integrate this. That's at squared, and I think it's over 2 as well. And then there's a divided by t squared. It's possible, I do watch me, I make mistakes. Last time I did this, there was a 2 there, but I think I did it wrong before. We can probably check that, because you can see there the 2's clearly cancel out, don't they? U is 2k times minus a over, yeah, that's right, I think we're right there. the 2 disappears. So anyway, so we'll just rewrite this here in front of the integral sign. So I'll just erase that and put the integral sign back in. So we've got 2k over a times t times the integral of e to the at squared over 2 all divided by t squared. And so u2 is equal to 2k t over a times, and I'm going to put the constant in now because I'll forget if I don't, at squared over 2 over t squared dt plus a constant of integration. Right, okay, let me cut and paste that. We should probably have been keeping equation numbers for these things. So let's just go back and have I been properly labeling my equations? So I think we'll call this equation 6. I think one of the last equations was equation 5. So that's equation 6. And can we get, no, we can't get rid of that now. Never mind. Okay, so we've got this equation, u2 is equal to that. Well, what is this integral? E to the at squared over 2 over t squared. And we're going to try and solve it. So let me just, my writing is, I'd like my writing to be neater, but anyway. So what I'm going to do is I'm going to take P equal, because this is the same as t to the minus, the integral of t to the minus 2 times e to the a t squared over 2 dt, right? So what I'm going to do is, let's just erase that and go back to that. We'll put P is equal to, well, we'll work out what P is in a minute. We'll put P prime equal to t to the minus 2, and P is equal to the integral of t to the minus 2, which is minus t to the minus 1. And then we choose Q to be e to the a t squared over 2. So Q prime is equal to 2t a over 2 e to the a t squared over 2. I think the 2's cancel, and I think if you do that, I think you run into problems because what I should have said was, before I did all that, I'd kind of forgotten that it's okay trying to do it by hand, but what you find is that this includes special functions like the exponential integral. This is an exponential integral as it stands, so we could just leave it like that. So what I'm going to do is I'm going to leave equation 6 on its own, and we're going to integrate. We're going to see what Mathematica gets for this integral. So if I just show desktop and go to Mathematica, let's just pause that. You've actually seen sort of what I was expecting to get. So we've got did I say that was 80 squared divided by 2? Let me just have a look. Right. Yeah, e to the 80 squared over 2. A to the e to the 80 squared over 2. Right. Now we're dividing that by t to the power 2. And that's what we get there. So let's just delete this nonsense, and we want to integrate this. There we are, Control V. So if we integrate that, we get this, I think it's an imaginary error function. So let me see if I can write that down. So we've got minus E so we've got U2 equals 2KT over A times, and I'm afraid I'm going to have to look at the Mathematica screen again, e to the 80 squared over 2, e to the 80 squared over 2, divided by t. I better not start putting plus minus signs in yet. Plus, well, I'm just going to combine this square root of a with the square root of pi over 2 together. So we've got plus a pi. So that's right. We want a nice big square root, don't we? A pi over 2. Yeah. Times the error function, the imaginary error function of, and what does it give? You've probably got a better memory than me. Square root of a over the square root of 2. I'm going to write it like that. Square root of a over the square root of 2t. And we've got, well, we'll put the constant of integration there. So, therefore, the general solution to equation 3, let's just go back and have a quick look at that. It is there, but I wanted, yeah. So this equation here in this page that got inserted that we didn't use in the end. So the general solution to equation 3 is U equals, well, shall we do this in blue, and then it breaks it up a bit. So U equals U1 plus U2, and that's equal to, well, we know what U1 is equal to, because that's minus 80 over 2k, whoops, equals minus a over 2k, and then there's a t there, minus, sorry, I'm making a lot of spelling errors. Well, just a lot of typos is the correct word. So it's minus 80 over 2k plus all of this in red. Well, we can simplify this. So we get plus 2k over a. The t, that that t cancels with that t, but so we're left with e to the at squared over 2 plus, we'll write it out in full, 2kt over a times the square root of a times the square root of pi. I see why it might have been a better idea to leave it all like this before, times the imaginary error function of root of a over 2t. Okay, so let's go to red. So we've got, therefore, u equals minus a over 2k times t. In fact, actually, let's write it the other way around. So we'll write this one first. So we've got 2k over a e to the a t squared over 2 minus a over 2k t. And then we want to simplify all of this. So that becomes plus, well, 2 divided by a root 2 simply becomes root of 2. A root of a divided by a, well, you get a root of a on the bottom, and we've got a k. So let's see, we've dealt with that, we've dealt with that, we've dealt with that, we've dealt with that. So we're just left with a k t there times the imaginary error function root a over 2t, and that is the solution. This can be simplified to give, and I'll just write it down very right. So that is root of 2 over a times kt times 0, and that is the general solution to equation 3. So I'll leave it to that for now, because I think I've gone on quite a long while. I tend to really labour on these videos, and I know that my videos take a lot longer than most other people's, even for the same quantity of stuff, and my memory isn't very good, so I spend a lot of time trying to remember things instead of just being able to write it down, and that's a problem. So apologies to those who are watching for the length of these sessions, because they do really go on for a very long time, a lot longer than I would like, and are very involved. And if I was someone else, I would be able to do it in about 20-25 minutes, but I tried and I've tried, I just can't get it down to those sorts of time spans. So many apologies, everybody, and I hope that that has been a good tour of how to solve a non-linear equation in equation 3 in order to get the final general solution there. So I'll leave it at that for now, and bid you farewell, and see you later. Okay then.